Okay, we've dealt with tangent. Now let's talk about the inverse sine function. We are going to run into similar problems with tangent, and we'll solve them in a similar way. So let's go ahead and look at the graph of the sine function. Here it is in green, and if you remember, let me get myself a pointer. If you remember, when the angle is 0, the sine is 0. And then the sine slowly increases until the angle pi over 2, or 90 degrees, the sine is equal to 1. Then it decreases again, and at the angle pi, or 180, it's equal to 0 again, and then it goes down, and so on and on. Now, question number 1. Is this function one-to-one? That is to say, if I give you an output, sine is equal to something, can you tell me one value of sine one angle, that when you take sine of that angle, it gives you this output? So let's look at an output. Let me see, sine of the highest is 1. Let's look at 1/2. In order to get an output of 1/2, well, we would have to plug in this angle here into the sine function. You see that guy right there? You may even know what that angle is. 1/2 is one of those values of sine which should somehow stick in your head. And we'll come back to that later. But the trouble is that that's not the only place where you get an output of 1/2. So if y equal 1/2, I could also go over here. There's an angle here which gives me an output of 1/2. And also way over here, you can see there's another one that gives me an output of 1/2. And back here, there's one. And here, there's one. And this shows you that if you draw a horizontal line, it crosses the sine function in many places. And that means that the sine function, as we know it, is not one-to-one. And so we're going to handle this. In order to have an inverse function, we need to restrict it in such a way that it becomes one-to-one. And so what we do is we just choose one part of the cycle where we can, if we just look at that part, we pass the horizontal line test. And in particular, we're going to start at the bottom here, just a little bit to the left. It's at negative pi over 2. And we're going to go up to the top, pi over 2. If we go over the top and down the other side, we're going to run into trouble because we're going to have a point here and here that have the same y value, the same output value. So in order to preserve one-to-oneness, we have to stop here. And the farthest we can go here is negative pi over 2 for the same reason. If we go a little bit farther, we're going to get places where we get a doubling up, same y value. So the domain we're going to deal with is from negative pi over 2 to positive pi over 2. That restriction, let's see, I've got it in already. Here. It's a little bit hard to tell the color difference, but it's the one part that is in red here to here. And in fact, I can get rid of the rest of it. We can just look at the red one. This is the part of the sine function that we are going to consider when we look at the inverse. This thing is one-to-one because any horizontal line hits this thing only exactly one time. And because of that, we can look at the inverse of this. So for example, this has a pair here where the angle, the input, the x is pi over 2, that's a 90 degrees, and the sine of that is equal to 1. And so if this is the x is pi over 2 and y is 1, when we look at the inverse function, we're going to have the x be equal to 1 and the y be equal to pi over 2. Now pi over 2, this is not set up to show angles so easily, but the number pi is 3.14, and if you divide that by 2, dividing 3 point something by 2 gets you 1 point something, 1.6, maybe 1.5 something. So the corresponding point to this one, which is pi over 2 comma 1, is going to be 1 comma pi over 2. It's going to be somewhere here. And every other point is going to go to the corresponding place on the inverse trig function, the inverse or arcsine function. Every x, y on the sine function is going to correspond, if you switch the x and the y, to a point on the arcsine function. So let's go ahead and see what that inverse sine function looks like. Here it is. If you look at both of them, you can see this is the point that ends up over here that I mentioned before. The point 0, 0 goes to the point 0, 0. And if you just want to look at this inverse sine function by itself, it is the one that I'm tracing here. I'll get rid of the original sine function so we can focus just on the inverse sine function. What is the domain and the range of the inverse sine function? Well, it's worth considering in the original sine function, the restricted version, it has a domain from minus pi over 2 up to pi over 2, and a range from negative 1 to 1. And when we look at the inverse function, we just switch those. So this one has a range from minus pi over 2 to pi over 2, and a domain from minus 1 to 1. And plugging something into inverse sine, if I pick a number like 1/2 and I plug it into the sine function, what I'm really asking is, what angle do I need to put into sine in order to get an output of 1/2? And we're going to talk about specific values of the inverse sine function when we look at examples. We'll do that next. Here we go. So, maybe observations first. When we write the inverse sine, we can write it either as sine with a little minus 1. Do not be fooled. That does not mean negative 1 power. We can also write it as arc sine, like so. They mean the same thing. And the definition is that y is equal to the inverse sine or the arc sine of x, provided the sine of y is equal to x. So when I write the inverse sine of something, what I'm asking is, what is that inverse sine equal to? I'm asking to find what is it that I have to plug into the sine function in order to get x as an output. And of course, because of the restriction to the sine function, this is only going to work if we have values of our angle that are within that restricted domain. And so the angle in this case is represented by the y. And so the values of the angle are y has to be in minus pi over 2 up to pi over 2. Okay. The other observation is that the inverse sine function is an odd function. And just as before, this means that if you would like to know inverse sine of a negative of a number x, you can find it by taking the inverse sine of the original x and making it negative. Being an odd function, the way I like to think of it when I'm working with it is it means you can pull a negative out into the front. Okay, we're going to use this observation, the fact that it's an odd function, together with our knowledge of the basic values of trig functions in order to work our way through some values of the inverse sine function. So let's take a look at the problem. Here at the top is our table of the trig values of various angles. And the example is this guy. The example, it has 5 parts, but you're going to see that these go relatively quickly. So, part A. What is the inverse sine or the arc sine of radical 2 over 2? Well, this is like saying, what angle do you have to plug in order to get the sine function to give you an answer of radical 2 over 2? And you can see if we look at our table, here are the angles at the top, and then here's the sine function. I happen to know the value radical 2 over 2 comes from a 45-degree angle or a pi over 4 angle. Here is the radical 2 over 2. And this is the angle it comes from. So sine inverse of radical 2 over 2, that's equal to pi over 4, or 45 degrees. Go ahead, pause the video, and try to work out B, C, D, and E. I notice there's a typo in part E. Let's just go ahead and fix that. Part E is supposed to say, what is the inverse sine of the number 3? That's what that's intended to say. Okay, so go ahead and give those a try, and then come on back. We'll work through them. So, let's look at B, sine inverse of 1. I'm just going to write this using the other notation, arc sine of 1, just to remind you that it means the same thing as sine inverse. Arc sine of 1 is like asking, okay, what angle has a sine equal to 1? And I know that it's the angle 90 degrees, or pi over 2. And you can see that in the table clearly here, arc sine of 1 is the angle pi over 2, or 90 degrees. So this is pi over 2, or 90 degrees. Let's see. Similarly, what is the inverse sine of the angle 0? Or the arc sine of the angle 0. What angle has sine of 0? Well, 0 has sine 0. As you can see here, the sine of x equal to 0 when the input is the angle 0, either in degrees or in radians. So this guy is 0 or 0 degrees. All right, moving on, part D. This is the inverse sine of negative 1/2. Now, for this one, we're going to use the fact that sine is an odd function, so we can pull the negative out in front. That's the negative sine inverse of 1/2. And this is like saying, okay, tell me what angle has a sine equal to 1/2, and then make that angle negative. Now, this is one we talked about looking at the graph. If you don't remember it, I just remember that 1/2 and radical 3 over 2 go together, and they go for the angles 30 and 60, and then I just have to remember sine is like the y on the unit circle, and 1/2 is the smaller of the two numbers, which means it will be the smaller angle, 30 degrees or pi over 6. If that chain of logic didn't compute in your head, don't worry, just look that when sine is equal to 1/2, the angle is pi over 6 or 30 degrees. And here, since we have that negative in front, we're going to keep that negative in front. So this is either negative pi over 6 in radians or negative 30 degrees. All right, that's part D. Part E. Part E says, find the inverse sine of the number 3. And for this one, it just helps to remember, like, what is the idea behind the sine, the inverse sine. For this, I ask myself, okay, what angle do you have to have that has a sine equal to 3? And the answer is there's no angle that works, because sine is never equal to 3. Sine is always some value between -1 and 1. And because of this, saying sine inverse of 3 just doesn't make any sense. So we would say this is undefined. All right, that's it for exact values of inverse sine functions. If you're interested in what happens when you put in other angles in here, ones that we don't know the exact values for, ones that aren't in the table, we'll be covering that at the bottom of this lesson. Thanks.